Curvilinear coordinate system 17. Consider a scalar function phi of position which depends on the cylindrical coordinates rho, phi, and z such that this function is equal to rho cosine phi, which is basically x using the Cartesian coordinates. So we were asked in part A to plot the surfaces of constant phi, and in part D plot the vector field lines on the same graph where the vector field lines are for the gradient of phi. So when we worked through this problem, we found that the radial and azimuthal components are cosine phi and minus sine phi given in cylindrical coordinates, and we have obtained rho of phi is equal to a constant divided by sine phi for rho as a function of phi in part D. Now, for the constant surfaces, since I'm going to plot this on the xy plane, I'm working in Cartesian coordinates, so this means phi is equal to x. So when I have phi is equal to x, f of xy is equal to x, I can do a contour plot, x between minus 5 and 5, y between minus 5 and 5, and then to find the x and y components of the gradient, I can use the grad command, and this gives me basically gradient x component is 1, y component is 0. That's not surprising because the scalar function is equal to x, its gradient is going to be equal to ex hat. Just the derivative with respect to x in ex hat direction. There is no derivative with respect to y. Therefore, we can plot this vector field using a vector plot, x component and y component between minus 5 and plus 5, and show them together. Now you can see that this phi of xy is equal to a constant value for each x here. X is equal to 0, it's a constant, x is equal to 2, it's a constant, etc. And it's increasing as I go to higher x's, decreasing as I go to lower x's, as expected. And on the other hand, the vector field v is just ex hat. So for all values of x and y here, I find that I have a vector, a unit vector that points in ex hat direction. So that's showing both the phi as a function of xy and vector field as a function of xy on the xy